had the pleasure of joining you all a couple of months ago. I'm Abbie Liel. I'm a professor in the University of Colorado Boulder in the Department of Civil, Environmental, and Architectural Engineering. I am today in my office. My sabbatical is almost over. And last time I was in my office a few days ago, the fire alarm went off for an hour. So we're hoping that doesn't happen today. Two of my colleagues are joining us here. Brennan Bean from Utah State University, and Ahmed Abdulal, who is now at, I'm going to try to get it right, Ahmed, SUNY Polytechnic in New York. Is that right?
Right. Yes.
Just moved from Texas A&M. And I'm going to describe on the next slide kind of their role. Ken Kunkel is also going to join us later, but he had a conflict for part of the time, who I think many of you know. So as I mentioned, I did speak with you all before, so my introduction is pretty brief. It's just going to try to remind everybody what we're trying to do and how kind of this conversation I think fits in. So just as a reminder, so I'm the chair of the Future Conditions Subcommittee of ASCE 728, Chapter 36. We are addressing at a minimum flood, snow, rain, ice, and wind hazards. And the future conditions of those hazards. ASCE 7 is about loads on buildings and non-building structures. So the intent here is to develop loads for these climate hazards into the future. The ones that are red are the ones that are represented by people on this call. So Ahmed, Brennan, and Ken. But I wanted to put flood and wind up there too. To let you know, we are doing those things. I just didn't want to overwhelm. Didn't want to try to fit too many things into a small time. I also put in this other bullet point to just kind of make sure, kind of clarify what we're trying to do. Is like we currently have no Chapter 36. It's a blank page, right? So we need to author text about all sorts of things, including when do these provisions apply. What kinds of, how do you combine these loads in the future scenarios, all kinds of things, in addition to some specific technical work on the hazards particular. So I wanted to kind of show how the data needs we're going to talk about today fit in this broader context of a lot of like writing and thinking and reviewing in order to get something that is an engineering standard that can be used to design building infrastructure. And this will come up again on the next page when I get to the timeline, but you know, the consensus review process for standards is, and no, don't use this in a critical way, it is an onerous process. It is time consuming and it involves a lot of kind of back and forth and feedback and work. And so when you see the timeline on the next page, the reason the timeline is like that is because we have to make sure, I as a subcommittee chair need to make sure that we have time to do all that other work, writing, putting it together, making the case to the profession to make sure that we are successful in this effort. So related to this group, when do we need the data? As soon as possible. But that doesn't mean, like, we are really hoping for and envisioning a back and forth. So that doesn't mean that we need it tomorrow and then we are hoping to never, you know, go back and forth again. I think, you know, we need some version as soon as possible. We need to understand the limitations, what might be coming down the pipeline, so we can start to incorporate that work into our workflow and really stay kind of parallel to any developments in climate models and climate scientists that we can feed in as we go forward. The critical date on the technical work side is early 2025. So ASCE 728 is published in 28, but that really means the technical work needs to be done in 2025 so that we can do all that other work to get that material into the standard and do some of the engineering packaging of that work that is necessary to be successful through that review process. And then I just have one more slide before I turn it over to, I think I'm Brennan, but just I wanted to remind everybody kind of the kinds of things we think about in the context of design standards. So we design for loads that have, we hope, a low likelihood of exceedance with the primary goal of low probabilities of failure. So this annual probability of failure I list here is one of the targets set out in ASCE 7. In the past, we have mostly developed these loads from data and extreme value statistics. We haven't heavily used climate models even for the past. So there's a transition both to going to models and going to the future that we're needing to think about as we move forward. The design loads in some cases need high spatial and temporal resolution. And so one of the things we're going to be grappling with is what is the necessary resolution for what we're doing in chapter 36. Just to remind everybody too, that we're thinking about the direction that chapter 36 subcommittee is going is a 3° C increase relative to the baseline and a 100-year building lifespan. So those are kind of the parameters that we're working within. And so what's going to happen next is that Brennan and Ahmed are going to share kind of what they're thinking on 2 of the specific hazards. And they are researchers who are also on the committee. So they will be helping us with and leading the snow and ice part of the chapter. So they're doing a lot of the technical work and also contributing to the authorship and the committee. So with that, that's my introduction. I don't know if we want to take questions or just move on, Dan.
My recommendation would be that unless somebody is totally confused and needs a clarification, we just move on and hold questions for the end.
Great. All right, so now you should see Brennan's slide.
Yeah, I'll do a quick sound check. Can everyone hear me okay?
You're good.
Yes.
All right, so this is just a brief introduction to what we're doing with snow, what we hope we could have in terms of data with snow, but also recognizing the reality of the situation and hopefully proposing a feasible path forward. So what we've been doing is we've been collecting historical annual maximum snow water equivalent values. When we say annual, we mean by water year, so like July to July, so we have a full snow season. At measurement locations across the United States, this is what we used to develop the most recent version of snow loads in ASCE 722, so about 7,800 different locations that had enough historical annual snow water equivalent values to fit a probability distribution. If we go to the next slide. And so we take these annual maximum values, we fit a generalized extreme value distribution. We make sure that those fits are right. We do some regional statistics in order to get the shape parameters correct. But the key here is that we have annual maximum snow water equivalent. We translate that to a load using the maximum density of water and fit these probability distributions to then get what we call a reliability targeted load, which, if we go to the next slide, is simply pitting a distribution of load, which is a combination of the amount of snow water equivalent on the ground and the anticipated percentage of that, whatever's on the ground at its maximum, that is retained on the roof. Because and that's an engineering thing that we're not trying to address with the NOAA data, but we take a distribution of resistance and a distribution of load, we pit them against each other, and we come up with a snow load value that achieves a uniform probability of structure failure. And so what this image is supposed to illustrate is that the MRIs are not constant. Now ignore these actual MRIs because this is a highly simplified scenario. But the key is that as the resistance distribution stays, well, right now we assume it stays exactly the same, but it stays relatively constant across the country, that we have similar confidence in steel made in Maryland as we do in steel made in Utah. But the environmental hazard varies drastically. And so the relative variability of the environmental hazard to the structure is what causes the MRI to shift, because we're not targeting a uniform hazard or like extreme event, we're targeting a uniform probability of failure. Next slide. So after we do all this engineering magic, we get a map, and this is a contour map, but it's also in a geodatabase, which is represented on the right. 1 kilometer resolution is what we've been targeting. You type in your address, and at a 1 kilometer resolution, we give you a single value. In this case, it's ironically showing wind, not snow, but it gives you a single value that is your design load for whatever hazard of interest in snow. We get it from this 1 kilometer resolution grid. Next slide. What we wish we had, and I am under no illusions that this is going to be available, but I figure it kind of like sets the tone for if we were living in, you know, our imaginary world, what we'd want, and then we can talk about what we think we can use. And that would be high fidelity projections of an annual maximum snow water equivalent dynamically downscaled to 1 kilometer resolution. And I'm not a climate scientist, but I've done a lot of digging with the proposal that Abbie and I are part of to look at this, funded by NOAA. Dan Barry's the program coordinator. To know that computationally, what I just said, that sentence is not feasible right now. But in our perfect world, this is SNODAS data. It's a 1 kilometer resolution. We could just comb all of that for some future period and get an ensemble of projected annual maximums, and then kind of just plug and play with everything that we've been doing up to this point. So that's what we wish we had, but we do not expect. What we think we need, which is the next slide, this is the proposal that we submitted last November. That's the start date is in September 1st. I don't want to go into the details there. My opinion is that I am kind of assuming that we'll take whatever NOAA has available. We've got the SSP 8.5, the 8.5 scenario available by SPEAR. We've got CMIP 6, which has other scenarios, that we're just going to take the data that's available to us as is and make an attempt to use it to get close to what we wish we had, which we know we can't have. So creating statistical models that maybe relate precipitation and temperature to annual maximum loads, given that we don't necessarily have, or at least I don't think we have, high fidelity, the ability to get high fidelity annual maximum snow water equivalents from climate models at a 1 kilometer resolution. So we're going to create these models and do that in a first iteration. And what I think we need is feedback after we've attempted that. So here's what we did. So I feel like we need to do something first on the ASCE side, but then having a moment to say, here's what we did, what is wrong with that? And that dialogue lets us then go back and make a second iteration. And I think that's going to be the key here, is that we try something rough and quick to see what the holes are in what we're doing. And that might also help NOAA identify easy opportunities for, oh, well, we have that information, we just don't publish it. Like, here you go, let's do that. And we make marginal changes to then do a second iteration that hopefully would be suitable for a first pass in ASCE 7. And that's the end of my presentation. And it looks like Allison has a question. I don't know if that's for me, but I'm happy to answer.
Question is for you. Thanks for that great presentation. And someone asked if you could share the slides, and I hope you can. I had a question about your methodology, the slide that's up here. You said you're going to sort of take what's available, do what you can, and then ask for feedback on that. What is your process for getting feedback? Is that publishing it in the scientific literature and using that as a way to vet it? Are there climate scientists on your team? Do you have colleagues at universities who have, or other places that have agreed to review? Like, what's sort of the thinking there?
Just real quick, Allison. I think in the interest of getting through these, can we hold your question to the end? Because
Absolutely.
You might have a similar question for the other two. And I just know how we all are, you know, it
That's
might
totally
not be
fine.
a quick and dirty. Okay, excellent. And Dan, how about you? Can yours wait, or is it something you need before we move on?
Oh, sure, I can wait. I'll just note that I have to get off the call at 1, so
okay.
All
right,
Thanks, Dan.
I'll hold your spot. Okay. All right, Abbie, back to you.
Okay, so the next thing I'm going to show is, just give me a second, Ahmed's slide. And then I'm going to do my best to present Ken's work, and then he's going to show up in the second hour so we can ask him questions.
Okay, sounds good.
Specific questions, but at least you'll have the introduction. Okay, so, all right, I'm going. Let's see.
Because we are going to have a discussion at the end of these about how to move forward. So we should have plenty of time to discuss it.
Okay, so you should see a slide that says ice load hazard planned work now, yes?
Yes, yes. So mine is going to be too short, just one slide. So I'm going to start first. So if you can click, Abbie, it's kind of like they have some animation. So this is showing the current maps that exist in the ASCE 7. So the ice load hazard If you can click more, Abby. So you can see that these maps are showing the nominal ice thickness by freezing grain. When we speak about ice load, we have two different types. We have in-cloud ice and we have freezing grain. This code is focusing more in the freezing grain. And as you can see, this one is showing just one map. It's showing it's built by the ArcGIS, kind of like trying to use the historical data from weather station across the United States, trying to do some statistical analysis using some ice models. And then we are using this to build these maps. For sure, to do this one, you need to have a lot of data, and we have some data that we need to kind of like try to play with it, try to make it, or try to make it as feasible or as good as possible, because not all data that we need is available. We submitted a proposal. We try to do our best to get some funding for that, and we're going to speak about why we need to have some funding. But we submitted a proposal for the DRRG, which I see that the winners are already announced. But if you click more, Abby, so if the planned work is we're trying to get some data for the future. So if we're trying to do this, or if we did this in the past, how can we start to do this in the future? So Maritai, which is in this call, she is our climate scientist. She kind of like told us about the NA Cortex and the data that we can extract from that, and we can get data from 1950 to 2100. If you click more, Abby. So this is the NA Cortex maps, and then this is covering 48 states and also Alaska. So we can get all of this data. We can start to get data from 1950 to 2100. We can start to compare the data that we have from the weather station versus the NA Cortex. So kind of like trying to evaluate and validate the data from the NA Cortex versus observational data, kind of like trying to see the accuracy and trying to get more accurate information, have a good comparison between the NA Cortex data and the observational data. But the next thing that we need to do is taking this data, trying to run it for the future. As I mentioned, we're going to try to get it for the 2100, trying to use the data that we're getting for our icing model. The icing models are equations that we are using to be able to get the equivalent radial thickness. Then we started to run an extreme value analysis, and then trying to get the extreme value or extreme ice thickness and the concurrent wind speed. And based on that, we start to kind of like having an idea about what's going to happen in the future as we move forward. So the data that we needed, if you click forward, Abby, so we need to have precipitation type and amount, wind speed, air and dew point temperature, and downwelling solar radiation. So these are a lot of work, because we need to have this data for every 3 hours daily, and then we need to do some analysis to do that. So it needs to have a lot of work, but first we need to get the data. To get the data, and Mari is in this call, she can speak about the effort that this need to be done. And then once we get this data, we need to do the validation, and then we need to run this for the future. So we need to have a lot of funding to be able to do that. Again, as I mentioned, we're trying to do our best to get some funding to run this work, but without funding, this work will not be possible. We need to have some stuff to push stuff forward. Abby give the deadline or the timeline that we need to have. We have 2025, 2026, and right now we're 2023. So we need to start as soon as possible. We have in the team Kathy Jones as well. She's the one that did this historically in the past for the weather station. Again, the plan is to do this for the future. How we're gonna move this forward? Again, we need to have some data, and that's gonna be the biggest question mark, or the biggest thing that we need. How can we get more funding to be able to move this work forward? So again, I'm trying to make it short and summarize all of the work that we do. But again, we need to have something that can push this work forward, which we need to have some funding. And that's all for me, Abby. Thank you.
Thank you, Ahmed. So Dan, shall I proceed to Ken's slides, and then we can see if there's time for questions?
So. Yeah, that way we can
Okay.
have a good time for discussion.
Okay, so on the rain load side of things, we have Ken Kunkel, who has some funding from the Climate Program Office at NOAA to work on this, and so he put together a few slides describing what his team is planning to do. So the first slide is about the challenges the first one, and apologies to those of you who are climate scientists, since I am not, but I will summarize how I understand the issues. So challenging with understanding how heavy rainfall and this 15-minute increment of rainfall, which is the parameter that we use in ASCE 7, scales with temperature. So needing to understand that, and that the difficulty in using a lot of the climate simulations because of the coarse spatial resolution in understanding that process. And so their team is proposing to use cloud resolving climate models that are run at these small scales to investigate those trends, and then use that to understand how we might understand how rainfall is going to change in the future for this 15-minute increment. So just, and then the last bullet point in this slide is just acknowledging the computational intensive nature of that particular kind of climate model. So necessarily understanding the problem with those models, and then later, I'm going to use the word scaling, but applying that to understand the problem more broadly. So one of their key efforts is the analysis of these simulations that are readily available. This is describing some of the data and models they're planning to use, and they have the historical simulation data already, and expecting to be able to obtain the future simulation data when it is completed. They also are working in developing using some data from the University of Illinois, and currently working on a subcontract to make sure that happens. So then the issues that Ken identified, and I think their team is on a good path, and they have a way forward. The issue identified is the subcontract and the timing on that, to make sure that they have the data as soon as they can get it. So that concludes Ken's slides, and as I said, he is going to join us. So if you have specific questions for him, we can discuss those later.
All right, sounds good. So I guess with that then, basically we have two presentations, as I mentioned earlier. This one is focused on the needs of ASCE 7, Chapter 36. Shirley's going to talk in a few minutes about what's going on water resources, primarily with stormwater. So what I'd like to do now is allow people to ask questions of the speakers so far. Something to keep in mind is what we're trying to work up to is a workflow process for NOAA to support these efforts and try to address some of these needs. The latter half of the session today is going to be exploring how do we do that? Should we have a workshop? When would that workshop be? How close can we get? More of a holistic approach. So right now, I think what we really want to focus on are these individual tasks, if you will, and questions to the speakers so far. So with that, I know Allison had her hand up, but Dan, you've got to leave here shortly. So maybe if Allison's okay with it, I'll let you go first, and then
It's
we'll
totally
go to
fine with me
Allison.
if Allison finishes her questioning.
And you're on, go for it.
Okay. Well, first of all, Abbie, Ahmed, and Brennan, it's really nice to meet you in a synchronous fashion. And I also appreciate you breaking your own news about your project being selected for funding. It's very frustrating for me that I really can't talk about the projects until all of the awards are accepted. So thank you for doing that. And the presentations were great, and really wonderful to see you talk about the projects and also the needs, as Ahmed was going into. I had a couple of questions for you on the project and the way that you're approaching some of the work. One of the questions was more kind of on Brennan's part of the presentation, and talking about like using generalized extreme value theorems theory to approach the issue of extremes and snow loads and snowfall and things like that. I was wondering to what extent you're also going to entrain some kind of process understanding or insight into some of the analysis. A lot of the work seems to be kind of around looking at pre-industrial, post-industrial, or looking at climate change and the influence on things like snowfall and snow load. But one of the things that we see with these extreme events that often challenge infrastructure is that they're just like the only thing that has ever happened in the PDF way on the right-hand side, if you think about those charts that Brennan was showing. And they often arise through a unique nonlinear combination of, some sort of natural variability or common meteorological system with perhaps more water vapor in the atmosphere or something like that at a process level that leads to something that's kind of unexpected in the historical framework. And then you get these really outlandish return interval values for those events when you do a post hoc analysis. So I was just wondering, are you also kind of thinking about some of the process drivers of extremes in particular regions? You put up Baltimore. I was kind of thinking about that. For example, you might have a typical nor'easter that just gets really loaded up with water vapor in a way that it would not have in a, early 20th century climate. What if a model is not identifying that type of a storm? How do you tackle that type of thing when you're thinking about the design extremes? So that was one question that I had. And then if I could also ask a second question after you process that one, that would be great. Thanks.
Sure. So I'm sure I haven't thought about it as deeply as you just described. I do know that when we even just looking at historical data, in a generalized extreme value analysis, the shape parameter becomes almost a function. Well, it's primarily a function of the time to maximum. So if you're in the mountains, you get these kind of light snows, relatively light, that happen over an extended period of time. So you almost kind of like, well, your shape parameter kind of goes to zero or even negative in those situations, versus in Baltimore, the maximum is being generated by only one or two storms, which leads to this highly variable, heavy tail shape. So in some way that kind of tracks process in that it's a combination of like individual storms plus time to maximum. As far as like anticipating future processes and how they affect like the tails of those probability distributions, that's something that we hadn't anticipated tackling, mostly because we were coming at it statistically, given this need to do it for the entire continent very quickly and being, computationally strapped to do that. But I think this kind of reinforces the need that we have, which is we'd like to make a first pass doing things quick. And the question you asked is the exact kind of question that we would like to entertain from an iteration 1 to an iteration 2. But we want to get an iteration 1 out there so that we can like discuss those kind of questions, maybe in more specifics relative to what we've already tried.
Yeah, like in a future proposal.
Yeah, even that, I was thinking within proposal, but definitely a cross proposal as well.
I mean, one of the things that might be helpful is, we're forming this task force, which you'll get info on hopefully soon. And there are going to be a lot of other scientists on the task force who are dealing with extratropical cyclones and nor'easters and phenomena like that. And there's a good opportunity there as well for some kind of cross-pollination and information sharing across the project. So that may be helpful as well to some of your analysis.
Absolutely. And then you have another question as well?
I did, yeah. This one was more for Abbie. So Abbie, you kind of touched lightly on this third rail of what scenarios to select, which is a can of worms that I think we've successfully largely kept closed so far in this interaction between NOAA and ASCE, although it's come up a few times. And it's great to hear you kind of decisively say that you're really interested in this 3-degree warming scenario. I was just wondering if you have more thoughts about how, or information about how you got to that point, and this issue of scenario selection and how current it is versus how like the ASCE 7 community, SEI and whatnot, from your perspective, have kind of arrived at an asymptote of being interested in this particular scenario of 3 degrees. It's something that, we've been talking with Ben and Dan Walker about maybe having a workshop to think about the scenario selection process a little bit more and having that kind of practice to practice discussion. But it's certainly a can of worms that could potentially derail a lot of the work that we're trying to do, and something that we do have to think through. So I'm really interested in how you were able to arrive at that, and your thoughts on scenario selection and that practice to practice issue.
So that really, SEI held a series of workshops on climate related issues kind of in the lead up to kind of setting up the future conditions subcommittee, which had a lot of structural engineers and a lot of the people on this call as well. The thought with there was some discomfort in choosing a specific emissions scenario, and wanting instead to go to a warming level. And so the conclusion from those workshops, and Jennifer can jump in here if she has anything to add, but the conclusion from those or the direction given from those workshops to the subcommittee I'm leaving was those kind of 100-year 3°C world. Now that's coming from a group of structural engineers. And so how that's operationalized, I think there's a lot of questions about how that might happen. And also whether, but to the extent possible, and I think this will be also discussed by the Future Conditions Subcommittee, but to the extent possible, I think we're recognizing that we need to not change the starting point, or 2025 is going to be impossible goal to meet. So the intent is to stick with that direction, but to kind of think through how we actually can reach that goal. Also recognizing that the work being done for this chapter is going to be done by a lot of people, some of whom have quite a bit of funding, some of whom have less. And so it's quite likely that there will be differences in how some of these ground rules are interpreted across the hazards, and that probably at this stage we're going to probably live with that, just because it's not like there's it's a community effort where we as the subcommittee are taking what we can get from a lot of these researchers doing amazing work. And so I don't know, Jennifer, did you have anything to add to that?
Yeah, I mean, Abbie's 100% right, Dan. And I'm sure there's others on the call who would love to have that can of worms open, but we purposefully tried to say, here's where we're going to start. We don't know everything, but we know that we want to be, we don't want to be too conservative, but we also want to be able to account for some things that are beyond what we're considering right now. And so as engineers, we took our best guess at what we think would be possible from a document development standpoint and said, here's where we're going to start. And so we're going to use this, and we're going to use the 100-year lifespan, which is also different from the assumptions in the base document of ASCE, which is only 50. So we just made that educated decision early on based on the timelines that we had to accomplish the work, knowing this was our first pass, and that was the direction we're going to go forward on. So to Abbie's point, we needed to start somewhere. So this was our starting point, and we can't keep going back to the beginning and changing the assumptions, or we're just never going to get there by 2025. So that you're kind of seeing how the sausage is made in a standard document development. We have to use our best engineering judgment for many of our decision making, and this was one of them.
Yeah, I mean, I think it's great. Honestly, I think 3 degrees from a climate science perspective, and Joe or others could weigh in on this, is probably quite a reasonable approximation of where we're headed at the moment without significant policy changes or technology development changes. And the fact that you've been able to get some acceptance of that to sort of circumvent all of the policy and political conversations that come along with the actual scenarios, which have a whole different valence around them. I think that's right. That's not something to take lightly, that you've been able to achieve that, and whether to question that too much, actually. But I appreciate the background, Abbie and Jennifer.
Okay, so Joe, I have a feeling you're much on the same vein. If you can make it kind of quick, we will have more time to explore this later. I just want to make sure we get to Shirley. So go ahead.
No, I just wanted to say, I'm about the global warming levels. It's really kind of important to suggest that the word global warming level be used there, because some people think 3 degrees means 3 degrees locally, but 3 degrees globally tends to mean about 4 or plus degrees over land. So, Celsius. So just making sure that the semantics on that are really clear, if that's what you want to go, where you want to go. And I suggest everyone read the 2-page summary in the IPCC technical summary, AR6, that talks about global warming levels versus scenarios as adaptation targets. It's a really excellent 2-page summary of the reasoning and climate science behind that. If you want to really delve into that. That's all I wanted to suggest, is I'm supportive of it, but it does open its own cans of worms once you start It's a radical departure from the way most people have done adaptation, quite honestly. And I think it's great. I think it short circuits a lot of problems you would run into otherwise, but keeping in mind that it is a bit of a radical departure from the way, reclamation has done it with their large scenarios and large ensembles and other groups. So, well, I'd be there to, I think Mary and I will be there to support you with that decision, but it's not.
Joe, would you drop that link for the reference you just cited?
I will, because I think it's just a really nice, from a climate science point of view, so you have to be on the climate
I'm
science.
happy to be educated. Again, thank you. Appreciate that.
It's a great summary.
Perfect.
All right, excellent. Ben, I see you got your hand up.
Yeah, thanks. Really, these presentations were really, really excellent. And it's just, there's a lot there that there's a lot there to chew on for sure. I have a two-parter also on the scenarios question. It seems on the one hand, the choice to frame the future work in 3 degrees, I agree with Dan, given where we are and given the complexity of scenario choice, I think 3 degrees is reasonable, makes a lot of sense. And it seems that should ensure kind of apples to apples approaches and comparisons when looking at future assumptions for rainfall and snow and ice. But I guess my question is, given the approaches that you are considering, will it be apples to apples? You have an approach for snow, approach for rain, approach for winds. In the end, I guess that's a question. In the end, will there be an apples to apples comparison in terms of the underlying kind of climate scenario or climate forcing, behind those different approaches? That's just big question number one. And then secondly, on rainfall, does the Ken Kunkel approach by default, is that your plan B if the Atlas 15 isn't ready in time?
So I'll start with the apples to apples approach. I mean, I think, our intent is to be as apples to apples as possible. Of course, when you go to different hazards with different levels of information, different needs from the engineering community, I think necessarily there will be some, like the ground rules will be the same, but what we do with them will be somewhat different. And so, this already, this is the standard is a community-based project where, the different hazards have different traditions of how they've dealt with the historical data as well. And so as apples to apples as possible. And it's certainly like that's, we're headed that way, but it's not a big organization doing all the work themselves, right? It's a very diffuse process. And so we have to, make sure that we're maintaining that comparison at the critical junctures and, also using all the information that's available. So I don't know if that's a very satisfying answer, but that's, I think, where we're headed on that piece.
Let me, before you go to the second piece, Abbie, I just want to make a real quick comment. Shirley Clark's presentation is going to be talking about, rainfall issues related to stormwater. So, what I'm hoping for is a process that as the work is done to advance Atlas 15 or the work that's done to support ASCE 7 chapter 36, we don't have a separate lane to do rainfall for stormwater. So, I think this whole discussion of scenarios and time horizons, it could be informed by some of the work that we're doing on these stormwater standards that Shirley's talking about. So just everybody kind of keep that in mind. All right. But go ahead. You had a second point there, Abbie?
Okay, so Ben, I'll attempt to answer your question about the Atlas 15, and then we can confirm with Ken. But my understanding is that he wants to better understand the relationship between the 15-minute and other intervals of rainfall regardless of whether Atlas 15 is available. And then the intent is that the work there would be able to slot in the Atlas 15 updates when it becomes available. So it is like preparing some of the relationships between like the interval, the time of rainfall, and the intensity, so that when the Atlas 15 is available, that could also could readily be incorporated. I don't know if anybody else has something to add to that, but that is my understanding.
Okay, Allison, I think you're up. Thank you for being patient.
Yeah, no worries. I still have the same question, which was directed towards Brennan, but could perhaps be applied more broadly, which is understanding sort of the vetting process. Brennan, you specifically mentioned, that you would look to do that, but I wasn't quite sure what the mechanism was and what kind of scientific or technical support would be needed for that, or that you would like to see for that kind of activity.
Yeah, so within the project that Abbie and I will be working on, we've got climate scientist Wei Zhang from Utah State University, who's part of that team. Recent change, but another snow hydrometeorologist, Dan McAvoy from Desert Research Institute. So within project, there are people with that expertise that we'll be getting feedback on for iteration 1. There's already mechanisms in place with this ASCE 7 process for us to get lots of feedback, probably more than I want, depends on the meeting, from engineers about that information and how it's presented. What I think we need, which we don't, I think, have a mechanism in place, but I think the potential is here given this working group and some of these other ongoing projects, is the opportunity to present interim findings at some type of venue like this to get feedback, very much like the question that Dan Barry asked me. Well, have you thought about this? Well, I hadn't really thought about it. And being able to try something and get that kind of feedback, that mechanism's not in place, but I feel like we're a half step away from being able to put it in place.
And to add to that, Brennan, I think you're not envisioning that you would send out publications and get or envisioning something more informal than like a peer-reviewed public. And I think there's broadly a comfort with sharing preliminary results potentially before publication,
absolutely, yes.
So the idea is an informal mechanism in a certain sense. I didn't want to make sure I'm not speaking for you, Brennan, but I think
thanks for clarifying, Abbie. That's what I meant.
Okay, so that was really helpful just in thinking about the different kinds of assistance we could provide. Much appreciated.
Yeah, thank you. Thanks for asking.